All right, so today we're going to look at polynomial functions. You know what polynomials are. You've seen them for a long time. You probably haven't actually seen the official definition because it looks really, really scary. But this says a polynomial function is a function in the form, and then there's this stuff that looks like a hot mess. But I don't want the hot mess to freak you out, because I could have something like f of x equals 3x to the fourth plus 2x cubed minus x squared plus 5x plus 7, or whatever. Okay, so that is a polynomial. So that is a polynomial. So I want to make sure that you understand why it's written like this, because this basically covers all polynomials ever. Another polynomial is 3x squared plus 2, right? And so your a to the nth power, that would be here, n would be 4. So a to the fourth. So a sub 4, or a sub 1, right, is going to be, this is the 3. This is the n minus 1, n minus 2. So n minus 1, n minus 2, and so forth and so on, all the way down to when you don't even have an x at all. Okay, so that's just that's your generic, it looks horrible, don't let it freak you out, okay? The coefficients, a sub n minus 1, a sub 1, and so forth and so on, are real numbers, and a sub n cannot equal 0, and it is a positive integer. No negative exponents. So this is really the biggest thing right now, no negative exponents in a polynomial. Make sure that your exponents go from greatest to least, and you can skip them, like maybe there isn't an x cubed term or something like that, but it's what we've been factoring. It's your polynomials, okay? So let's talk about shape and continuity of a polynomial, right? So polynomials, poly meaning many, nomials meaning terms, so many terms. It's not a monomial like we did yesterday, it was just one term, okay? Polynomials are smooth curves with no breaks. Oh, goodness. Which means it's continuous for all real numbers. Okay, so we talked about continuity before, and we would have like jump or whole point, discontinuity, that sort of thing. Polynomials are all continuous. So if I put my pencil down, I can draw the whole thing without picking it up. And the reason it says smooth curves, it's not pointy like an absolute value. There's no pointy. Everything is a curvy curve type of thing. Okay. The degree of the polynomial, so the highest exponent n is the degree and then they are classified by degree. Oh my gosh. They meaning the polynomials. They are classified by degree. Okay, so it's always the highest exponent, not necessarily the first. If they're in the correct order like they're supposed to be, then it would be the first one. So if we look down, we start down here. 8x to the fifth power. So this is the first one, and these are in the right order. That goes 5, 4, there is no 3, that's fine. Then a 2, 1, 0. So 5 is the first, but be careful not to fall in the trap of always picking the first. Make sure 5 really is the highest exponent, okay? So the degree here, since 5 is the highest exponent, is 5. The degree here is 4, 3, 2. This degree is 1, because we don't put a 1 there on the x normally, but it is there. This degree is 0, because this could be 2 times x to the 0 power, and anything to the 0 power is 1. Okay. So then when we classify them, when you have x to the 0 power, or it's like just f of x equals 2, that is your constant function. We know that this would be linear. What do we call a second degree? Quadratic. What do we call a third degree? Cubic. Good. And then the fourth degree fourth degree is quartic, 4 quarts in a gallon, right? Fifth degree, what do you think that is? Quintic. Okay. And the rest of them, they all have like hexic. There's names for all of them. Really, it's fine to call it a fifth degree, a fourth degree, a third degree polynomial, just as long as you know what you're talking about, okay? So we're going to talk about end behavior yet again. So we had that on the bottom of yesterday, so we have it here again, but we're going to look at it a little bit differently. And we're not going to write the words. So every time we've talked about end behavior so far, we've said, as x approaches infinity, f of x approaches infinity. The words are still important. But the pictures, the little pictures we're going to draw, they're important as well, because we're going to start sketching this stuff. So the power and coefficient of the leading term, okay, whatever your leading term is, determine the end behavior of the function. So recall that when we were looking at the monomials yesterday, if it's squared, if it was just the power function, it looked like a quadratic. If it was cubed, if it was even, it looked like a quadratic. If it was odd, it looked like a cubic. So the middle behavior changes when it's not a monomial. Okay, so like I said, we're going to start talking about middle behavior here. We don't really care about the middle behavior right now. That will look different, but the end behavior will still be the same. So if I have a function that looks like this, if I have a function that is like f of x equals 3x to the 4th plus 2x squared, something like that, okay? Then right now, I do not expect you to know what it looks like, okay? You don't know what that graph looks like as far as, parent functions and stuff are concerned, but what you do know is the end behavior. This is a positive leading coefficient. This is an even exponent. So the end behavior looks exactly like it does if it was just a quadratic. So your end behavior looks like this. We don't care about the middle right now. So as far as telling me end behavior, you're literally going to draw the arrows. Up, up. Okay? If I have, so that was even power positive coefficient. If I have an even power negative coefficient, so let's say this was f of x equals negative 3x to the 4th plus 2x squared, then it's an even power, which means my end behavior models a quadratic, so it's either up, up, or down, down. Since it's negative, it gets reflected, and it would be down, down. Okay. My odd power positive coefficient, I think about a cubic. All right, so I think about what this looks like, and let's say I had f of x equals 4x to the 5th minus x squared plus 2. Okay, I don't expect you to know what that graph looks like right now at this point, but you should be able to tell me the end behavior. Your leading coefficient is positive. This is odd. It's odd, so the ends are opposite. It models a cubic. And since this is positive, it models the positive cubic, so the end behavior would be down, up. And then odd power negative coefficient, so let's say that's f of x equals 4 times, negative 4. That doesn't even look like a negative 4. Negative 4, we'll still just do x to the 5th minus x squared plus 2. You have no idea what the middle behavior looks like, but this is odd, so the ends are opposite, and it's negative, so it follows a negative cubic, and the ends, we know, do this. And you'll see why tomorrow that's super important that we know that. It may seem silly right now, but... And then again, the words are still important. I should still be able to say, as x approaches infinity, f of x approaches negative infinity. As x approaches negative infinity, f of x approaches infinity. That's still important, but the pictures are going to be important for us too. Okay, we good? Awesome. All right. So now we're going to just identify these. So it says, using the leading term, give the end behavior of each polynomial function. All right. So this is an even number, right? An even number, so it's going to model a quadratic. So that means it's either up, up, or down, down. What do you think this would be? since this is even, so yeah, so it's negative, so it would be down, down. That's literally what you get from it. Okay. And it might not be a bad idea, maybe not so much the quadratic, but the cubic, to like have one drawn off to the side so you can keep the down, up, down in your mind correct, so that you don't get it backwards. So this is, I can't even read that number. Mine are all blurry. What is that? Well, this is negative 2x to the what? Fifth? Okay. So this is odd, which means the sides, the ends are opposite. It's negative, so it gets reflected from this, so it would be up, down. Does that make sense to you? Why it's like that? It's only the ends. We'll figure out the middle tomorrow. All right, so you do 3 through 6. And I'll get a piece of paper where I can actually read what those numbers are. It does not transfer well into here, and they just blobs up here. Daniel, are you asleep? Let me put you on the naughty list. Okay, let's see who's going to help. Daniel, can you tell me what number 3 is going to look like? Up, up. Y'all agree with that? Yes, very good. He did that one in his sleep. You should be proud of him. Good job. All right. Adrian, what about number 4? Down, down. What's this number right here? 7. Is that even or odd? Odd. Odd goes with the odd numbers with cubic. Don't look at the 4. The 4 doesn't matter. Okay. It is, so it is down, up. Make sense? Okay, good deal. That's why we're doing these. All right, Leo, what about number 5? God, I can't read that number. I think you're right. 3, yes. Down, up. Good job. And then Jose, tell me that last one. It is down, down. Do we all agree with those? Any questions about why that is what it is? Remember, odd is opposite, so it's got to be up, down, or down, up. Odd is opposite, even is the same. Okay, we good? So we're going to do the same kind of thing here, but it's basically the opposite. They give us the picture. So it says, describe both the power and coefficient of the leading term of the polynomial given. So I'm going to say whether it's positive or negative and whether it's even or odd. So if this is the picture I have no idea how to write the equation right now. I don't expect you to know that. But when you look at the end behavior, the end stuff, the ends are opposite, right? One's up, one's down, vice versa. So is this even or odd? Odd. So this would be an odd power. Do you think this would be positive or negative coefficient? Remember, think of your cubic parent function looks like that. Is that the same, or did it get reflected? It got reflected, which means that this is a negative coefficient. Okay, does that make sense to you? Negative leading coefficient, odd power. All right, so you do number 8. All right, Adrian, is my power even or odd? Even. Very good. And then Leo, positive or negative? Positive. Very good. What questions do you have? And you understand the words I'm using, what the leading coefficient is, what the leading term is, what the power is, the degree. We get all those terms? Yes? Okay. So let's talk about turning points, which we've already talked about a little bit with our maximums and minimums, but we're going to talk about it a little bit more here. It says the points at which, so the turning points, the points at which a polynomial function switches direction. We go from increasing to decreasing or vice versa. If the turning point is higher than any nearby point, okay, remember how we talked about the points in its neighborhood, then that makes it a relative maximum. If the turning point is lower than any nearby point, it is called a relative minimum. All right. So I want to, I'm going to draw another little picture here. Let's say that I had this. Okay. How many relative maximums do I have? 1. This would be a relative maximum, right? How many relative minimums do I have? 2. How many absolute minimums do I have? 1. So remember, your absolute minimum is also a relative minimum, right? Because we might only be looking at this point, and so it's both. I just want to make sure, because that seems a little confusing sometimes. Okay, maximum and minimum values. They are called, so they're part of critical points. Do you remember what they're called? It was a weird plural word. Starts with an E. These are maximums and minimums are extremes, so they are extrema. Extrema. And turning points define where a function is increasing or decreasing. So we talked about that when we talked about increasing or decreasing. And we've talked about relative maximums and minimums. I just wanted to remind you that an absolute was also a relative. And then this next part actually says using the calculator to find turning points. We are not doing this because the reason we would have to use a calculator is because it requires calculus to find them by hand. But if we do it on the calculator, I'm going to tell you push this button, this button, this button, and it spits a number at you. You have no idea why and what's the point, okay? So when we sketch the polynomials, we're going to be sketching them because we won't be able to find the maximums and minimums, and that's okay. You need to know what they are and basically where they would be, but we're not going to find them exactly. That's not a pre-cal thing, okay? Any questions at all? Good deal.